Did you know you could use the mean value theorem to get information about a function f when you only know information about the derivative of that function f prime? Yeah, let me show you how that works. Here we're given, G-I-V-E-N, that the function evaluated at 0 is equal to -3. Okay, we do know something about the function. We know an ordered pair on the function. It's the ordered pair xy equals 0, -3. And the derivative, f prime of x, is always going to be smaller or equal to 5 for any x value on the real numbers. That's important. So we know something huge about the derivative. We know one little point on the original function. From that information, we're going to be able to tell you how large the y partner to x equals 3 can possibly be. F of 2, how large can that be? I'm not talking about f prime of 2. I'm talking about f of 2. So I'm taking that f prime of x is less than or equal to 5 for all real numbers and using that along with the ordered pair for the original function, xy equals 0, -3, to tell you the maximum value we can get for the y partner in the function for f of 2. Okay, well, we have f prime of x is less than or equal to 5 for all real numbers. That's given to us. Well, that would imply that f prime of x exists. If it's less than or equal to 5, it exists, for crying out loud, for all x values. So that means that f is differentiable for all the real numbers. That's exactly what it means. And that implies that f is continuous on the real numbers. By note number 41, differentiability implies continuity. Thus, we are allowed to apply the mean value theorem to any subset closed interval from a to b. It's a subset of all real numbers. Now, or open subsets too. So let the closed interval of x values from a to b equals 0 to 2. Why did we choose a equals 0 and b equal 2? Well, we were given that f of 0 equals -3, so we know something about x equals 0. And we seek data about f of 2. That's where x is equal to 2. So we let a equal 0 and b equal 2. Now, the mean value theorem says there's going to exist an x value named c, somewhere between 0 and 2, such that the derivative evaluated at that x value c is going to be equal to the difference quotient, f of 2 minus f of 0 over 2 minus 0. In other words, f of 2 minus f of 0 over 2. Well, move things around on that equation. Move the f of 2 minus f of 0 to the other side, or get it alone. It equals 2 times f prime of c. Now isolate f of 2, which we want to talk about. It's equal to 2 times f prime of c plus f of 0. Okay, so that means f of 2 is equal to 2 times f prime of c plus a -3. Why? Because I told us f of 0 equals -3. Okay, now, we know that f prime of x is always going to be smaller or equal to 5 for any value x. Thus, for our value x equals c, it of course will be true that f prime of c will be less than or equal to 5. Okay, so take the line we had above, bring it down here. That would imply that f of 2 is less than or equal to 2 times 5 minus 3. See, I replaced f prime of c with something that's less than or equal to it, so the f of 2 is less than or equal to 2 times 5 minus 3, which simplifies to 7. So I found that f of 2 is going to be less than or equal to 7. What does that mean? It means the largest that f of 2 can possibly get to be is 7.